Hi, welcome back to College Algebra. In this week we're going to talk about how to factor and solve polynomial equations, and also we'll introduce rational expressions. We'll cover 4.7, 4.8, and 5.1. As always, please look over the measurable outcomes for the week. Okay, let's talk about how to factor binomials. And we've seen this actually previously when we discussed factoring, but this is the factor form of a difference of squares. If you have a squared minus b squared, then that is you can factor that into a plus b and a minus b. And so, for example, 16x squared minus 9. Notice that we need this to be a square and this to be a square, and then this to be a difference. So we need to find what a is, and then what b is. So b is going to be 3 and a is going to be 4x, because 4x squared is 16x squared. So once we realize that, we can now apply our formula. Oh, by the way, before we try any factoring technique, we should always look for the greatest common factor. There's actually there's no common factor between these two, so the greatest common factor is just 1. But if there was a common factor, then we need to factor that out first before we try any techniques. And we saw that in one of the previous lecture. And so the GCF is 1, so we don't have to worry about that. So now we can apply the formula. So again, 4x being squared is 16x squared, 3 being squared is 9, so a is 4x, b is 3. Now let's apply the formula, which is a plus b, so 4x plus 3, and then 4x minus 3. So this is similar here, except that again, we always should want to look for the greatest common factor. So let's do that first. Notice that there's a 2 between that we can factor out of the 98 and 50, and then between the variables, there's no c in both terms. There's a d term here and also d cubed, so we take out the smaller term, which is the d term. And so 2d is the greatest common factor. We pull it out, and this is what's left. And notice now this is the difference of square, because this is a square, this is a square, this is the difference. And so again, 7c squared is 49c squared, 5d squared is 25d squared. So now we can apply the previous formula to 7c and 5d. So again, 7c plus 5d, 7c minus 5d. So this one looks like the power is the fourth power, so but we can do the same technique. Again, there's no GCF here, so the a term in this case will be z squared, because z square is z to the fourth, and then 9 squared is 81. So our a is z squared and our b is 9. So applying the formula, we have z squared plus 9, z squared minus 9, and then we notice that this part right here is the sum of squares, which means that we actually cannot factor this, whereas this part we can factor. We do the same technique, which is that this is a difference of squares, so this becomes z plus 3 and z minus 3. So this is the full factor form of this binomial. So again, as I mentioned just now, when a and b have no common factors, the sum of squares is not factorable. So in other words, a squared plus b squared is prime. So for example, x squared plus 9. So it looks like this might be factorable, but again, this is a square, this is a square, but when you have a plus or an addition between them, then we can't factor that. Similarly, this is a perfect square, this is a perfect square, but this is a sum, so we cannot factor it. Similarly here, these are perfect squares, but we can't factor that as well. Okay, so this one is very optional. We can also factor sum and difference of cubes, and so we have to kind of memorize this formula, but for this class we don't have to memorize it. We see that you have a sum of cubes or difference of cube. We can look it up, and then we can factor by looking it up. But a couple things to notice is that this is a plus, and so this is also a plus. This is a minus. This is a minus. Then in here it switches the plus to minus, minus to plus, and then this is always plus. So if you want to memorize it, you can. But so this next example is optional. If you're going to go on to pre-calculus or calculus, then definitely knowing how to factor something like this would be important. But it won't be tested in this class. So here's the example to illustrate this. So again, we can write this as a cube and b cube, and this is the difference of cubes. So a would be 2x, because 2x cubed is 8x cubed, and then 3 cubed is 27. So basically cube rooting these values, and then now we can apply our formula, and that is a cubed minus b cubed is this formula. So we're going to substitute in a is 2x, b is 3, so we can just say 2x minus 3, 2x squared plus 2x times 3 plus 3 squared. Simplifying, we get this, and that's how we factor the sum, the difference of cubes. Okay, let's look at what is a quadratic equation. So a quadratic equation is an equation that involves the three constants a, b, c, and it has the form ax squared plus bx plus c is 0. So you want to be able to solve this quadratic equation. So we have to be careful that sometimes things might not look quadratic, but if we write it in a certain way, it will be quadratic. So for example, this for example, I can move the 1 over, and this form match up with this form exactly. Same thing here. It looks like maybe, again, this 0 is very easy. All we have to do is just bring everything on the left. So for example, I can distribute this x squared minus 2x, bring the 3 over, minus 3. That's a quadratic equation. Same thing here. You multiply everything out, distribute to get x squared minus 16, bring the 9 over, and then now this is quadratic as well. This is actually one of the most important rules that we have in just basic math. This zero product rule. It tells us how to solve equation, and essentially most of math is trying to solve equation. So if you have an equation that's equal to 0, and we can factor the lefts into a product of a and b, then that means that either a is 0 or b is 0. So again, if the product of a and b is 0, it must be true that at least one of them is 0, one or the other or both. So this will help us solve the equation. So the key is that when we have any equation, we want to put everything on the left to make it equal to 0, because 0, notice, because of this zero product rule, we want the equation to be 0, and then we can factor this. If we can factor this, then we can use this rule to break it down to two equation, and then we can solve them individually. So for example, let's solve this. We're going to bring everything on one side so that we can have it in quadratic form. So there it is, minus 12. Now we want to solve factor this. So again, we spent a lot of time factoring in the last couple of lectures, so it's important to know how to factor a quadratic. So again, using techniques we learned previously, we can factor this quadratic into 2x plus 3, x minus 4. Again, we can do try and error method or the AC method that we discussed earlier. So again, factoring is super important, because factoring is a very important part of solving equation, especially if we move on to other math classes. This is something that we really have to master. And so once we factor this, we have that the product of these two expressions equal to 0. So that means that either the first one is 0 or the second one is 0. And now we have two equations that are simpler than the original. We can solve them separately. And so 2x plus 3 equals 0 means that x has to be negative 3 halves. And in the other case, x has to be 4. So those are my two solutions. So here in this case, we want to factor this, and notice that this is very simple. We just got to factor out the common, greatest common factor. We can pull out 2x from both of these, and then now either the 2x is 0 or 3x plus 4 is 0. If 2x is 0, x must be 0. In the other case, x must be negative 4 over 3. So these are the two equations, the two solutions. So this looks more complicated, but it's the same thing, where we have to just simplify the algebra. So maybe we can distribute this and move everything on one side. So for example, I can distribute this to clear the parentheses. You get 36x squared plus 18x, and now we can move everything on combine like terms and move everything on one side. So combine like terms here, 18x minus 10x is 8x. Then put everything on one side, we get this, and now we can factor this. This is actually the sum of I guess difference of squares that we just saw. So this is 6x minus 5, 6x plus 5, and then again, either this is 0 or that is 0, and so either x is 5, 6 or negative 5, 6. Okay, what if we have a higher degree polynomial? So far we've seen a lot of quadratic. Well, it's the same idea. If things can be factored, we can always use the zero product rule. So in this case, this example is simple because everything is factored already, which is usually not the case. But if everything is already factored, we can apply the product rule, and even if this is more than 2 terms, the product rule still works. The zero product rule still works. So again, if all these things multiply equals 0, then at least one of them must be 0. Well, if all of them equal 0, then we can make them 0 by setting each of them to be 0. And so so either this is 0, or this is 0, or this is 0, or that is 0. Because any of those would make the whole thing 0. But negative 2 cannot be 0, so that's no solution. Y plus 7 is 0 means y is negative 7. Y minus 1 being 0 means y is 1. And then 10y plus 3 being 0 means y is negative 3/10. So that means that that we have 3 equations to this problem. Okay, so here's a cubic we want to solve. So something that, if you have a quadratic, we want to just use the technique we saw earlier, the AC method, just that reverse Fourier method. But if you have something that's higher, so one thing to try is to try factoring by grouping. And so let's take the first 2 terms put on this side, the second 2 terms put on this side. Again, one of the tricks we saw earlier was that we group this because 3 divided by 1 is the same as negative 12 divided by negative 4. So if you see that kind of a ratio, that's how you want to decide that you're grouping. So factor this out, the z square out, and that's the greatest common factor. The greatest common factor here is negative 4. Factor that out, and notice that if I do that, I have a common term. That's how you know that this will work. So now factor out the z plus 3, and we have z plus 3 times z squared minus 4. This is the difference of square, so I can break that down into z minus 2 and z plus 2. And now these 3 products equal 0 mean that either this is 0, where z is negative 3, or this is 0, where z is 2, or this is 0, where z is negative 2. So those are 3 equations. So here's an application of this. So suppose you have let's look at a basketball court, and so it turns out that the length of the basketball court is 6 feet less than 2 times the width. So if this is the width, then the length is 2 times the width minus 6. So we want to so because of that restriction, and also it's the fact that the total area of a basketball court is 4,700 square feet. So knowing that, can we find the dimension of this basketball court? Yeah, so here's our setup. Again, if w is the width, 2w minus 6 is the length. So the area is length times width. The area is 4,700, which is given. The length is 2w minus 6, and the width is w. So you multiply this out, you get this quadratic. So now we got to solve this quadratic by so put everything on one side so that we have the whole equation equals 0. Now there's a greatest common factor between all these, which is the 2. Everything's even, so factor the 2. And now we can factor this by using, again, that one of the method we saw earlier, w minus 50 times the w plus 47. That might need a little bit of a calculator work, but there it is. And then so now either w is 50 or w is negative 47, but we can't have a negative w, so it must be the case that the width is 50 feet, and then to find the length, you plug it back into the length formula, which is 2w minus 6. So that means the length is 94 feet. So there's the dimension of the basketball court. Okay, so now we know how to solve quadratic equation. Let's talk about quadratic function. So you have a function defined by this ax squared plus bx plus c, then that function is a quadratic function. So we're actually going to spend more time on this at the end of the course, the end of the semester. So right now, I just want to briefly talk about this quadratic function. So the graph of a quadratic function is a parabola. So either faces up or faces down. It doesn't have to be centered at the origin here, but it can move around a little bit. But this example is the x squared, the simplest quadratic, which is x squared, and this is its negative. If I negate this function, I get the reflection over the x-axis. But it turns out that the coefficient a tells you how this parabola is gonna opens. If a is positive, the parabola is gonna open up. If a is negative, for example, in this example, the parabola is gonna face down. So again, we'll spend some more time on this later, but Suppose that I have a quadratic function. So here's the quadratic function. We want to find the x and y intercepts. In other words, if I were to graph this, here are the x intercepts. So we're basically looking for these 2 points, and here's the y intercepts. So finding x and y intercepts is very important. And so let's see how we do this with this problem. We've seen how to find x and y intercepts for linear function, and so this is for quadratic functions. And so again, to find the x-intercept, we want to know the x-intercept has the property that y is 0. So we set the equation, the function is the y value, make that equal 0. And now we can solve this equation by factoring, for example. So if I factor this out into x minus 4, x plus 3, either x is 4 or x is negative 3. So the x-intercepts are at 4, 0 and negative 3, 0. So this is negative 3, 0 here, and this is 4, 0 on the right here. To find the y-intercept is actually easier to find. The y-intercept, all you have to do is plug in x is 0, because when x is 0, you get the y-intercept. So that means I plug in 0 for x into the function, and I get negative 12. So the y-intercept is 0, negative 12. Okay, here's an application of a quadratic function problem. Suppose you have a rocket that is shot vertically upward with a certain initial velocity, 288 feet per second. So again, when you shoot something up straight up, and that object is subjected to gravity, the function that model its height or its distance from the ground is quadratic. And so again, there's actually a physics way to justify that, but we won't go into the detail of that. So suppose that here's the height function of this rocket, and so again, the height is measured in feet, and time is measured in seconds. So let's look at these problem. But what does that mean to plug in 0, 5, 10, and 15 to the function? Let's see if we can do this one at a time. So if I plug in these point, that means I'm plugging in the time. So when time is 0 second, the height is 0. So that's the beginning of the rocket. When time is 5 second, the height is 1040, etc. So you plug in these points, then the key is that you get the height at the corresponding time. And so, for example, when the height is 15 from the picture of 15, when time is 15, the height from the picture is 750. So this point right here denote the height of the rocket. Okay, how do you interpret the x-intercept of the function? That's the second question. So the x-intercept of the function is essentially where the function touches the x-axis, in this case the t-axis. So the x-intercept is this point right here and this point on the right, and so that corresponds to when the rocket is on the ground, because when the height is 0, that means it's on the ground. So if I solve this equation for when the height is 0, then I'm trying to figure out what time is the rocket on the ground. Well, so again, here's the factor. I just get a factor of the GCF, which is 16t, negative 16t, and so you get that either t is 0 or t is 18. When t is 0, that's where the rocket is initially, which is at the ground level. When t is 18, that means that the rocket has gone up and then stopped and then comes back down because of gravity. So that means that 18 seconds pass before the rocket comes back down to the ground. And then another question is, when you solve an equation like this, h of t is 1152. You're trying to figure out at what time is the height at this 1152 feet above the ground. So I'm setting the height to be this number, and then again factoring again, put everything on one side. This is GCF here of 16, and then factoring this to give you t minus 6 or t minus 12. So either t is 6 or 12. That means there's 2 times where the height is 1152, and that makes sense because you look at the model of this rocket. It goes up to the highest height, stops, and then it comes down. So that's so that means that it's going to hit at 1152 at 2 places, on the way up and also on the way down. Okay, let's talk about rational function. So this will be the last section here. Function is rational function if it can be written in the form px over qx, where px is a polynomial and qx is a polynomial. We saw that earlier. And qx cannot be 0. So here's some of the rational function. 1 over x. Notice 1 is a linear function. Degree 0. X is the linear function, degree 1. Well, actually, rather 1 is a constant. But so notice same thing here. This is polynomial, so is this a plus 7, a squared minus 5. So notice everything is a polynomial divided by a polynomial. One of the important questions about a function is to find the domain of a function. So how do you find the domain of a rational function? Well, the domain of the rational function is very simple. It's essentially that everything is allowed except for the fact that you cannot divide by 0. So you find out where the bottom is 0. Those are the places that is not in the domain, because we're not allowed to divide by 0. In other words, the domain is essentially all the points where the denominator q of x is not 0. So one way to do this is to well, first of all, here's a function, and if I were to plug in, now here's a rational function. If I plug in these points, I won't really go into this, but then just make sure you know how to essentially plug it in and divide. So these are all the different points for the function. Notice that most points are okay, except that when you plug in 3, you get this problem of 2 divided by 0. You can't divide by 0, so that means 3 is undefined. That means 3 is not in the domain. So what is in the domain? Well, again, this is very simple. The idea is that we need to have the denominator not being 0. So one way to do this is figure out when is the denominator equal 0. So x minus 3, when is it equal 0? When x is 3. So that means when x is 3, it makes the denominator 0, so that means the 3 is not in the domain. So that means that we have to exclude 3 from the domain. So that means the domain is all real numbers. So you want to use set builder notation. Then the set of all x such that, vertical line, x is a real number and x is not 3. We are excluding 3 from our possible values for the domain. Use the interval notation from negative infinity to 3, not including 3 with the parentheses. Union 3, not including, to infinity. This is how you exclude 3 using interval notation. So the domain is everything except for 3. Okay, let's find the domain of these functions. So again, the domain is basically when the bottom is not 0. And so let's figure out when let's solve it for when the bottom is 0. So set the denominator be equal to 0, factor into 2 parts, 2x minus 1, x minus 5. So x is either 1/2 or x is 5. So those 2 points are not in the domain. So the set of our x is that x is not 1/2, x is not 5 is the domain of this function. You can also write this as interval notation. You gotta make sure you go from you not include these 2 points. So negative infinity to 1/2, not including, union 1/2 to 5, not including either endpoint, union 5 to infinity, not including 5. Okay, so what's the domain of this function? Again, when is the denominator 0? We want to exclude this point. But notice x squared is always going to be non-negative, because you can have negative. X squared is always non-negative. Non-negative number plus 4 is going to be positive. So the bottom is always positive, meaning it's always bigger than 0. So it can never be equal to 0. So therefore that means that there's no points where this is 0. That means all points are allowed, and so the domain is all real numbers. So negative infinity to positive infinity. That's because there's no point in the real number that will make the denominator 0, because this is always positive. So the domain is all real numbers. Okay, let's talk about how to simplify rational functions. So let's start by talking about how to simplify a fraction. So we have 15 over 35 and a factor 15 and 35 into 3 times 5 and 7 times 5. Notice the 5 can cancel, and that's how we can simplify a fraction. So this works the same way for rational expression or rational function. You factor the top and bottom. So for example, x plus 3, x minus 4, the bottom is x plus 4, x minus 4. The x minus 4 can be cancelled, just like the 5 can be cancelled. Then we have a simplified expression. So here's the principle. The principle here is that we have p, q, r, which are polynomials, and we have that r is on top as well as on the bottom. And as long as r is not 0, we can cancel r, so that we can simplify the rational expression. Now, one thing we have to be careful is that a rational expression is not defined for the values where the denominator is 0, and so we have to make sure that we put a restrictions on our variable so that the denominator is not 0. So for example, here's the rational expression. let's figure out what the restriction for this function as well as the simplifying it. So let's factor the numerator and the denominator. There's a common factor here, 2x in all of these at the top, so I pull it out. And then there's also a common greatest common factor between the bottom, which is 6. Pull that out. And so I factor the top part. And now try to factor again. X squared plus 6x plus 8. That's a quadratic that can be factored into x plus 4, x plus 2. So now we notice that we can cancel this. But before we cancel, we have to be careful that we know that. Let's look at this restriction. What is the restriction on this rational expression? Well, the denominator cannot be 0. Look at this. The denominator is 0 when x is negative 4. So that means negative 4 is not allowed. So we have to make sure we know the restriction ahead of time before we cancel. Again, because we want to cancel this to simplify, but before we cancel, we have to know the restriction. Because if we cancel it, we don't see it anymore. We might mistakenly believe that there's no restriction on x. So let me kind of explain that. So again, if I make the bottom be 0, then I get that x is negative 4. That means that negative 4 is not allowed, is not in the domain. So x is not equal to negative 4. So that's the restriction on this rational expression. So now we can simplify it by canceling. But again, so if I cancel this, I get a simplified expression. But notice that when I cancel, I might mistakenly believe that the original function is equal to this function for all x. But that's not true. These two functions are equal only if x is not negative 4. Because if x was negative 4, we have a 0 at the denominator, and that's not possible. You cannot divide by 0. And so so knowing that restriction before we simplify is very important, because we need to be clear that this function is only equal to this function if x is not negative 4. Otherwise, we have that problem dividing by 0. So again, just to reiterate this point, this function and the original function that we had earlier, and then the simplified expression, they only equal to each other. They're equal for all value of x, except for when x is negative 4. Because when x is negative 4, the left side have 0 at the bottom, which is undefined. The right side is actually okay. When you plug negative 4 on the right side, you do get an output, a value, but on the left side, we have an undefined number. So they're not the same when x is negative 4. Okay, let's do another example here. Let's factor the top. Notice the top is actually a sum of cubes, and so we can use the formula we saw earlier to factor the top. And now we have this quadratic, which we can try to factor again. And then the bottom is a simple example of the sum of the t and 2 being square. So again, this is we saw in the last lecture how to factor something like this. T plus 2 squared is t squared plus 4t plus 4 is one of those special forms that we saw in the last lecture. And so now we can try to factor again the top part, which is another quadratic. Well, in fact, before we do that, let's we notice that we can actually cancel t plus 2 here and this t plus 2. So we cancel that. We have this, and also one last thing is that, well, if we try to factor this this term, we can try and error, try to factor this term, but we see that this term is actually not factorable, so that we can't factor this further, and there's no more. We can't simplify this any further. So this is the final form. Okay, well, one last technique before we end is that sometimes it looks like an expression is not you can't simplify, but it turns out that if you look carefully, we might have two factors that are opposite. We can pull out a negative 1 so that it can be factored, it can be cancelled. So negative 5 divided by 5 is negative 1. So the idea these terms are opposite, so when you divide them, you get negative 1. But here's what I want to point out is that x plus 7 and negative x minus 7, it looks like these are different, and it looks like we can't cancel, but we can if we look at it carefully, and that is, look at the bottom. Let's take out the negative 1. If I take out negative 1, and suddenly this is x plus 7, and we can cancel to get negative 1 at the end. So this says that we have to be careful and see that the top and the bottom might be opposite, and if that's the case, then we can cancel to get negative 1. So here's another example. Notice that 2 minus x is opposite from x minus 2. the way we know is that you negate everything. So the 2 negate 2 is negative 2, negating negative x is positive x. So notice the top and the bottoms are negative each other, and so that's the case. You get negative 1 because everything cancels except for the negative 1. So if we recognize these things, we can help us also simplify other rational expression. So here's one last example. So again, this is how I factor this. This is the difference of squares, so I can factor that into 5 minus x and 5 plus x. And notice it looks like if you look at, we're not careful, we might see, oh, maybe this cannot be simplified, but we can if we look carefully and see that x minus 5 and 5 minus x are opposite, so we can cancel it to get a negative 1. And so there's negative 1 here now, and we can take this negative 1 and put it on the numerator, or put it outside in front. So either one would be correct. Yeah. So again, the key here is that we might, if we notice that things are negative, we can cancel it to get negative 1. Okay. So one last thing to say is that here's a mistake that a lot of people will make when we try to simplify a rational expression. So on the left here, we can cancel the 3 because the 3 times x divided by 3 times y, the 3 can be cancelled. But on the right side though, these 3 cannot be cancelled. And again, the key is that on the left side, these are products. If you have products, you can cancel, but if this is a sum or a difference, then these 3 cannot be cancelled. This is a common algebra mistake. Okay, thanks for watching.